Everyone, I welcome you all to my YouTube channel. So it's been long that I have posted any video. Let us not waste much time and take up our last topic, which is left in the delocalization, different cases of delocalization. So we are taking the pi sigma free radical case today. This is the last type of conjugation that we have. I have taken only 2 questions because I think these will be enough to make you thorough with the delocalization process involved in this case. Okay, so this is the allyl radical. The first one is the allyl radical. Let us see how this is conjugated. Okay, this is a pi bond. Here we have a sigma bond, and this is the free radical that we have. Okay, now we are supposed to make the different resonance contributors of this compound, this radical. So whenever free radicals are involved, we show the movement of electrons via half-headed arrows. Okay, this is a half-headed arrow, like this you draw it, or this. You don't draw a full complete arrow because you are not moving an electron pair, you are just moving one electron. Okay, so you will use this arrow or this arrow. Okay, now when this electron comes here, this pi bond, which is made up of 2 electrons, breaks like this. One electron goes to this carbon, one electron goes to this carbon. Okay, you get a radical at this position, and since a radical is formed at this position, and at this position we already have a radical, so one radical and another radical, they two combine together and form a bond. So we have a pi bond here and this bond as it is. Okay, so this is a contributor of this. Okay, both of these contribute to the hybrid of this allyl radical, and we get the hybrid as this. Partial double bond character here, partial double bond character here, and we don't make partial charges in this structure because we don't have separated charges here. We just make partial radical here and partial radical here. Okay, so this is the hybrid of the above allylic radical. Okay, now next structure is, this is the next compound that we have to solve. Okay, this is nothing but benzyl radical. Just like we had benzyl cation, benzyl carbocation, or benzyl carbon ion, we have benzyl radical as well. Okay, so we have a benzene ring, a CH2 group where the C possesses a radical. Okay, so again this electron comes here via half-headed arrows. This bond breaks and gives one radical here, one radical here. Okay, double bond CH2, because you are getting a structure like this. One carbon has one radical and the other 2 carbons adjacent pi bond. When it breaks, it gives a radical at this position, a radical at this position. So we can make a bond here using these 2 radicals, or we can make a bond here to get the structure back that we started with. Okay, so instead of making a bond here, we make the bond here using these 2 electrons. Okay, that is what we are doing in the delocalization of free radicals. Okay, so here we have the radical left, a pi bond here, a pi bond here. Now this radical moves forward, this pi bond breaks to give one electron here and one electron here, and we get another bond formed between this carbon and this carbon. The radical comes here and double bond CH2. Okay, now this radical moves forward, this pi bond cleaves homolytically. This cleavage is just to show the delocalization of this free radical. Okay, so you should not think an actual homolytic cleavage happening here. It is just a way to show the delocalization happening throughout. Okay, a pi bond here, a pi bond here, a radical here, double bond CH2. Now when this radical comes here, this breaks, okay, and we get our initial benzyl radical back. Okay, now it's the time to draw the hybrid. Circulation of pi density and CH2 here, partial radical character here, partial radical character here, partial radical character here, and a partial radical character on CH2. So this is the hybrid. Okay, so now we have completed the different cases of delocalization. This was the last case left, and we have seen two different examples dealing with this delocalization also. I hope you are thorough with this delocalization concept. Now we have to take another topic which is really important in the resonance process, which deals with stability of different resonance contributors. Okay, different resonance contributors have different stabilities. Okay, and the study of stability of different resonance contributors is important, and I'll tell you why it is important in the next few slides. First, let us see what are the features that decrease the stability of a particular resonance contributor. Okay, I have written these are the 3 points that decrease the stability of different resonance contributors. So the first one is, if in any resonance contributor you have an atom with incomplete octet. Okay, if the octet of any atom is not complete, then that particular structure will be unstable. The second one is, if you have a structure with charge separation, that contributor will also be less stable. Okay, so it is always said that neutral contributors are more stable. By the word neutral here you mean uncharged contributors. Okay, uncharged contributors. The second point says negative charge. This negative means negative charge. Negative charge on an electropositive element or a positive charge on an electronegative element makes the overall contributor less stable. Okay, suppose if you have a structure like this, okay, and oxygen possesses a positive charge and carbon possesses a negative charge. Okay, then this structure will be less stable as compared to if you have oxygen with a negative and carbon with positive, because oxygen is more electronegative than carbon now, and carbon here possesses a negative charge. What should be the case? Oxygen being more electronegative, it should have higher electron density because it is better able to accommodate the extra charge. So that's why a negative charge on an electronegative element is stable. But if a positive charge comes on the more electronegative element, it makes the contributor less stable. Okay, if you ask me, out of these 3, which one makes the contributor most unstable? So it is the first point. Okay, if you have an atom with incomplete octet, it will make the resonance contributor least stable out of the other 2. Okay, these 2 are still manageable, but an atom with incomplete octet makes the contributor more unstable. Now we have some questions to understand these features completely. Okay, these are 4 questions that we have to solve. We have to draw contributors of the following and rank them in decreasing order of stability. So the first one is this: a carbocation, an allylic carbocation. Okay, so this is the first question. Let us see how we can draw the contributors. We have pi sigma positive charge delocalization here. So pi electrons move towards the electron deficient carbon center. Here carbon bearing a positive has incomplete octet. Right? This carbon has an incomplete octet, and since we are moving this pi electron density towards this carbon, we are stabilizing this positive charge by making its octet complete. But in the process of moving this pi electron density towards this carbocation, we generate another carbocation. Okay, this is a contributor of this structure. Okay, both these are contributors of the hybrid, which is, what is the hybrid? CH3 single bond C, CH3 single bond CH, single bond CH, single bond CH3. This is the basic skeleton. Pi electron density here and pi electron density here, partial positive here and partial positive here. Now you have to tell me, out of A and B, which is more stable, because you have to rank the contributors in decreasing order of this stability now. So out of A and B, you have to tell me which one is more stable. Okay, as you can see, in A structure we have one carbon with incomplete octet. In the B structure also we have one carbon with incomplete octet. So in terms of incomplete octet, we have, both the structures have incomplete octet. Okay, but this carbon is what type of carbon? It is linked, since it is linked to 3 carbon chains, 1 carbon, 2nd carbon, 3rd carbon on its sides. So it is a tertiary type of carbocation, and this carbocation, it is only linked to 2 carbon chains on its side. So it is a secondary type of carbocation. And you already know a tertiary carbocation is more stable than secondary. Okay, so which structure will be more stable? Structure A will be more stable than structure B. Okay, you have to know that the most stable contributor, out of all the contributors you draw in a structure, the most stable contributor contributes more to the resonance hybrid. Okay, here A is more stable now, so A will contribute more to the resonance hybrid. Okay, this hybrid will have more partial positive character on this carbon than on this carbon. Okay, now let us see, this is the next question. We have to draw resonance contributors of it. We have pi, sigma, pi type delocalization here, pi, sigma and pi. And you have a choice of moving pi electrons. Okay, you remember now, if you have a choice in moving pi electrons, always move the pi electrons towards the more electronegative element. Okay, En. So out of carbon and out of oxygen, oxygen's electronegativity is higher now. So this pi density will shift towards oxygen rather than moving towards carbon, which is less electronegative in fact. So this pi electron density comes here when this pi shifts here. So we have the contributor as this negative pi density here and positive charge here. Okay, this is one contributor. Okay, here you have charge separation and you have a negative charge on electronegative element and a positive charge on electropositive element. Here this structure is neutral and charge separation is absent, no charge separation. So if these two are contributors, okay, this is contributor A, this is contributor B, and we are drawing the hybrid like this. Partial negative here, double bond character here, double bond character here, and double bond character here also, and a partial positive here. So out of A and B, which one will be more stable contributor and whose contributor will be higher in the hybrid? Let us see, let us try to answer this question. I have already written B structure has charge separation, A structure is neutral and uncharged. So of course A structure will be more stable than B and the contribution of A will be higher in the hybrid than B. Okay, so we have done this question also. Now we have this ester moiety. All right, this is structure A, and let us try to draw another contributor of this. When this pi this lone pair comes here, this is pi sigma lone pair type delocalization. Okay, when this this lone pair comes here, the pi electrons shift to oxygen. Okay, and we have this structure as the contributor. Okay, this is B. Now A structure is uncharged, B structure is charged, B structure also has charge separation. The same electronegative element, oxygen, has one oxygen atom has a negative charge, the other oxygen atom has a positive charge. So of course A is more stable than B because A is uncharged, B is charged. Okay. Now this is the next structure that we have. Here we'll have pi sigma negative charge delocalization. This negative charge comes here and the pi electron density is pulled away by oxygen. Pi density here, oxygen here, and negative here. And yes, this is the second contributor of this structure, and that's it. When this pi negative charge comes here, this pi electron will shift back to its initial position. Okay, if this is structure A and this is structure B, let us see which is a more stable structure out of these two, a more stable contributor. Here the negative charge resides on carbon, which is more positive than oxygen. Here the negative charge resides on oxygen, which is an electronegative element. Okay, so of course, if you see the tendency of accommodating the negative charge, oxygen is of course more efficient in accommodating the negative charge due to its high electronegativity. So structure B will be more stable than A. Okay, in all the structures you have seen how we are ranking different contributors. Alright, so structure B is more stable a contributor than structure A. So its contribution will be higher in the hybrid, higher contribution to the hybrid. And you can draw the hybrid structure very well. Pi density here, pi density here, partial negative here. Okay, this is the hybrid. Now let us move to some remarks that we have to remember. Okay, we have seen the stability of different contributors now, but we don't know why we are considering the stability of a contributor. Okay, the question is why the stability of a contributor is so important in resonance. Okay, so these 2 points answer this question very well. The more stable a contributing structure is, the more it contributes to the hybrid. Okay, जितना ज़्यादा स्टेबिलिटी होती है एक कॉन्ट्रीब्यूटिंग स्ट्रक्चर की, उतना ही ज़्यादा उसका कॉन्ट्रीब्यूशन होता है हाइब्रिड में. ओके, सो दिस आई ऑलरेडी टोल्ड यू. द नेक्स्ट पॉइंट सेज द एक्चुअल स्ट्रक्चर इज व्हाट? Actual structure is the hybrid structure. Okay, the hybrid has lower energy than even the most stable contributor. This is not hybrid, this is contributor. Okay, let me erase it. The actual structure has lower energy than even the most stable contributor. Okay, तो अगर कोई हमारे पास contributors है जिसमें एक कंट्रीब्यूटर काफी स्टेबल है, तो उस कंट्रीब्यूटर की स्टेबिलिटी से भी ज्यादा स्टेबल हमारा हाइब्रिड होता है. फॉर एग्जांपल, इधर बी सबसे ज्यादा स्टेबल कंट्रीब्यूटर था, लेकिन अगर आप एनर्जी कंपेयर करो बी स्ट्रक्चर की और इस हाइब्रिड की, तो इस हाइब्रिड की एनर्जी और भी कम होगी देन बी स्ट्रक्चर. ओके, ये और भी ज्यादा स्टेबल होगा बी कंट्रीब्यूटर से. दिस इज वेरी इंपॉर्टेंट. दिस इज ऑफन आस्क्ड इन MCQs as a conceptual question, so just remember these 2 points. The more stable the contributor is, the more it contributes to the hybrid, and the energy of a hybrid is lower than even the most stable contributing structure. Now we have a very, very important topic. It is the resonance energy or delocalization energy. We have been talking about resonance since for the past few videos, but we don't know what resonance energy is or delocalization energy is. Okay, so it is very important. Many questions have been asked from this topic in JEE exams also, or in JAM exams also. So resonance energy is, this is the definition of it. It is the additional stability a compound gains due to presence of delocalization. Delocalization energy, the DE and RE, these are the abbreviations for resonance energy and delocalization energy. So DE or RE depends upon few factors. The first one is this: number of equivalent contributors. Okay, the higher the number of equivalent contributors, the higher is the resonance energy. Okay, जितने ज्यादा equivalent contributors होंगे, equivalent मतलब सारे contributors सेम, सारे contributor structures सेम ही दिखते हैं. ओके, उनको इक्विवेलेंट कॉन्ट्रीब्यूटर्स कहते हैं. तो उन सबकी स्टेबिलिटी क्योंकि सेम होगी, सबकी एनर्जी सेम होगी, और जितने ज्यादा इक्विवेलेंट कॉन्ट्रीब्यूटर्स होंगे उतनी ही ज्यादा ओवरऑल रेजोनेंस एनर्जी होगी. ओके, सो आई हैव टेकन दीज टू एग्जांपल्स to make this point clear. This is the conjugate base of a sulfonic acid. सल्फोनिक एसिड फंक्शनल ग्रुप क्या होता है? SO3H attached to R group or TH group or anything. और ये क्या है? conjugate base of carboxylic acid. carboxylic acid, ठीक है, RCOO negative. So let us see out of these two which one has a higher resonance energy. ये दो conjugate bases मैंने लिए हैं, इन दोनों में से आपको बताना है कि किसकी resonance energy ज्यादा है. ठीक है, अब इधर O नेगेटिव है, पाई सिग्मा नेगेटिव चार्ज delocalization हो सकती है इधर, तो नेगेटिव चार्ज कम्स हियर, द पाई डेंसिटी इज शिफ्टेड टुवर्ड्स ऑक्सीजन. सो O नेगेटिव, डबल बॉन्ड O, डबल बॉन्ड O. अब आप देखो ये कॉन्ट्रीब्यूटर और ये कॉन्ट्रीब्यूटर दोनों इक्विवेलेंट है ना, क्योंकि इधर भी दो डबल बॉन्ड्स है, SO बॉन्ड के बीच दो डबल बॉन्ड्स है. देयर आर टू डबल बॉन्ड्स of two double bond linkages in between sulfur and oxygen and a single bond between sulfur and oxygen. इधर भी यही है, एक ऑक्सीजन के पास नेगेटिव चार्ज, एक ऑक्सीजन के पास नेगेटिव चार्ज, तो ये दोनों इक्विवेलेंट है. अब अगर ये नेगेटिव चार्ज इधर आता है तो ये सल्फर और ऑक्सीजन की डबल बॉन्ड शिफ्ट हो जाती है ऑक्सीजन की तरफ, क्योंकि सल्फर की इलेक्ट्रोनेगेटिविटी कम है ऑक्सीजन से. सो डबल बॉन्ड O एंड O नेगेटिव. तो ये भी एक इक्विवेलेंट कंट्रीब्यूटर हुआ इस स्ट्रक्चर का. तो ये तीनों इक्विवेलेंट कंट्रीब्यूटर्स हैं कॉन्जुगेट बेस के. तो 3 इक्विवेलेंट कंट्रीब्यूटर्स हैं सल्फोनिक एसिड के. तो लेट मी राइट 3 हियर. ओके, नाउ लेट अस सी कॉन्जुगेट बेस ऑफ कार्बोक्सिलिक एसिड के कितने रेजोनेंस कंट्रीब्यूटर्स हैं, इक्विवेलेंट कंट्रीब्यूटर्स हैं. ओके, सो R, CO and O negative. Again, pi sigma lone pair type pi sigma negative charge delocalization is possible. So negative charge comes here, this pi density shifts there towards oxygen. So oxygen has negative charge here and double bond is created between carbon and oxygen here. So these two structures are again equivalent because एक carbon oxygen single bond है, carbon oxygen single bond, oxygen के पास negative, oxygen के पास negative, and a carbon oxygen double bond is there, a carbonyl group is there. So these two are again equivalent contributors. ठीक है, तो सल्फोनिक एसिड के कॉन्जुगेट बेस में 3 इक्विवेलेंट कंट्रीब्यूटर्स हैं और कार्बोक्सिलिक एसिड के कॉन्जुगेट बेस में सिर्फ 2 इक्विवेलेंट कंट्रीब्यूटर्स हैं. तो किसका डिलोकलाइजेशन एनर्जी ज्यादा है इन दोनों में से? दिस हैज अ हायर डिलोकलाइजेशन एनर्जी ना. द कॉन्जुगेट बेस ऑफ सल्फोनिक एसिड हैज हायर डिलोकलाइजेशन एनर्जी और रेजोनेंस एनर्जी. जिसकी डिलोकलाइजेशन एनर्जी ज्यादा है वो ज्यादा स्टेबल है, और जो कॉन्जुगेट बेस ज्यादा स्टेबल होता है उसका एसिड ज्यादा स्ट्रॉन्ग एसिड होता है. तो अगर कोई भी पर्टिकुलर R ग्रुप है और उसका ही मैं सल्फोनिक एसिड देख रही हूँ और उसी का मैं कार्बोक्सिलिक एसिड डेरिवेटिव देख रही हूँ, ओके, इफ दिस R ग्रुप, सपोज दिस R ग्रुप इज मिथाइल, ओके, तो ये मिथाइल सल्फोनिक एसिड है और ये एसिटिक एसिड हो जाएगा। तो इन दोनों में से कौन ज्यादा एसिडिक होगा, दिस स्ट्रक्चर में से और इस स्ट्रक्चर में से, द वन whose conjugate base is more stable. So you have seen कि sulfonic acid, since it has 3 equivalent resonance contributors, it is more stable, and since the conjugate base of sulfonic acid is more stable, it is more acidic. These are some applications of resonance. Okay, acidic और basic character की I'll make a separate video जिसमें जब हमारे ये सारे concepts clear हो जाएंगे, even hyperconjugation, तो we will apply all the concepts all together to solve different questions. Okay, now the other factor which decides delocalization or resonance energy is the number of relatively stable contributors. Okay, जितने ज़्यादा stable contributors होंगे, stable by stable contributors mean कि या तो uncharged contributor हो, स्टेबल कॉन्ट्रीब्यूटर्स यू मीन कि या तो कॉन्ट्रीब्यूटर अनचार्ज हो या फिर अगर चार्ज है भी तो नेगेटिव रिसाइड्स ऑन मोर इलेक्ट्रोनेगेटिव एलिमेंट एंड पॉजिटिव ऑन द इलेक्ट्रोपॉजिटिव एटम, ठीक है। तो जितने ज्यादा स्टेबल कॉन्ट्रीब्यूटर्स होंगे उतनी ही ज्यादा इट इज डायरेक्टली प्रोपोर्शनल, दिस साइन मीन्स डायरेक्टली प्रोपोर्शनल, ओके। सो जितने ज्यादा स्टेबल कॉन्ट्रीब्यूटर्स होंगे उतनी ही ज्यादा रेजोनेंस एनर्जी हमारी इंक्रीज करेगी, ओके। सो दिस इज a carboxylic acid and this is carboxylic acid and this is the conjugate base of carboxylic acid, इसी का conjugate base है ये। तो इन दोनों में से पता करना है किसकी रेजोनेंस एनर्जी या डिलोकलाइजेशन एनर्जी ज्यादा है, ठीक है। तो हम कंट्रीब्यूटर्स बनाते हैं, ओके। जब मैंने इसको डिलोकलाइज किया इधर तो ऑक्सीजन पुल्स बैक इट्स pi electron density in the form of negative charge and this double bond comes here and this oxygen gets a positive charge, ठीक है। तो इधर चार्ज सेपरेशन हो गया। अब conjugate base of carboxylic acid के contributors हम देखते हैं, तो इधर negative charge comes here and oxygen pulls back this electron density to give a negative charge and double bond comes here। तो ये दोनों ही केस में चार्ज तो प्रेजेंट है लेकिन चार्ज इज प्रेजेंट ऑन द मोर इलेक्ट्रोनेगेटिव एलिमेंट और दोनों इक्विवेलेंट स्ट्रक्चर्स भी हैं, इक्विवेलेंट कंट्रीब्यूटर्स भी हैं, ठीक है। इधर ये कंट्रीब्यूटर तो न्यूट्रल है, अनचार्ज्ड है, सॉरी नॉट न्यूट्रल, अनचार्ज्ड है, बट दिस इज अ चार्ज्ड कंट्रीब्यूटर और इधर ऑक्सीजन जो कि मोर इलेक्ट्रोनेगेटिव एलिमेंट है, इट बियर्स अ पॉजिटिव चार्ज, सो ये इसकी स्टेबिलिटी को और कम कर देता है, डिक्रीजेस द स्टेबिलिटी। So here which structure will have more resonance energy, a higher resonance energy? Of course the conjugate base of carboxylic acid has a higher resonance energy if compared to the carboxylic acid alone, okay। So this has a higher resonance energy because it has a higher number of relatively stable contributors। ये दोनों ही contributors stable हैं क्योंकि negative charge ऑक्सीजन के ऊपर आ रहा है। इधर ये स्ट्रक्चर अनस्टेबल है क्योंकि एक जगह ऑक्सीजन तो नेगेटिव चार्ज कैरी कर रहा है बट द अदर ऑक्सीजन हैज अ पॉजिटिव चार्ज आल्सो। और अगर इन दोनों कंट्रीब्यूटर्स की बात करें किसकी स्टेबिलिटी ज्यादा होगी किसकी नहीं, इसकी स्टेबिलिटी ज्यादा होगी, दिस विल बी मोर स्टेबल, दिस विल बी लेस स्टेबल बिकॉज हियर वी हैव चार्ज सेपरेशन, हियर वी डोंट हैव एनी चार्ज सेपरेशन। नाउ द थर्ड फैक्टर इज अपॉन विच द रेजोनेंस एनर्जी और डिलोकलाइजेशन एनर्जी डिपेंड्स अपॉन इज द एक्सटेंट ऑफ कॉन्जुगेशन, ओके। जितना ज्यादा कॉन्जुगेशन होगी, जितना ज्यादा डिलोकलाइजेशन स्प्रेड होगी स्पेस में, उतना ही ज्यादा हमारा रेजोनेंस एनर्जी होती है या फिर डिलोकलाइजेशन एनर्जी होती है। हियर इफ यू सी देयर आर 3 पाई बॉन्ड्स, हियर वी हैव ओनली 2 पाई बॉन्ड्स, तो डिलोकलाइजेशन इन दोनों के बीच में ही पॉसिबल है, ये इधर जाएगा तो ये इधर जाएगा, और इफ दिस कम्स हियर दिस पाई बॉन्ड विल गो देयर, ओके। हियर वी हैव 3 पाई बॉन्ड्स एंड इस पूरे ही स्पेस में पाई डेंसिटी इक्वली स्प्रेड रहेगी or this has a higher degree of conjugation. ठीक है, तो जितनी एक्सटेंट ऑफ कॉन्जुगेशन ज्यादा होती है उतना ही रेजोनेंस एनर्जी या डीलोकलाइजेशन एनर्जी ज्यादा रहती है. द एक्सटेंट ऑफ कॉन्जुगेशन इज डायरेक्टली प्रोपोर्शनल टू रेजोनेंस एनर्जी और डीलोकलाइजेशन एनर्जी. सो आउट ऑफ, इफ लेट्स से दिस इज स्ट्रक्चर ए एंड दिस इज स्ट्रक्चर बी, if I ask you which one has higher resonance energy, then of course structure A has a higher resonance energy than B. Okay, resonance energy. Now let us see this question. Out of structure A and B, which ether has a higher resonance energy? Both of these are ethers na. So इसमें आप देखो, इधर pi sigma pi type delocalization and here pi sigma lone pair type delocalization is possible. तो थ्रू आउट इस सिस्टम में डीलोकलाइजेशन कंप्लीटली पॉसिबल है. ओके, हियर इफ यू सी पाई सिग्मा पाई इज देयर, बट देयर आर टू सिग्मा बॉन्ड सेपरेटिंग दिस लोन पेयर फ्रॉम दिस पाई बॉन्ड. सो डीलोकलाइजेशन सिर्फ और सिर्फ इस स्पेस तक पॉसिबल है. द डीलोकलाइजेशन हैपेंस ओनली इन दिस स्पेस, बट हियर डीलोकलाइजेशन स्प्रेड्स द pi electron density over all the atoms present. Here सिर्फ 1 2 3 4 चार कार्बन के बीच में, 4 एटम्स के बीच में डीलोकलाइजेशन है. इधर 1 2 3 4 5 एटम्स के बीच में. तो एक्सटेंट ऑफ डीलोकलाइजेशन इज हायर इन A स्ट्रक्चर ना. सो A has higher resonance energy than B because extent of delocalization is higher or more in A structure than in B structure. Let us see. I have drawn the contributors here. This is the first structure that we had. तो अगर ये lone pair, when this lone pair comes here, this pi density will shift to this carbon. This is the second contributor and this is the third contributor. So if you can see in both the contributors, we have a positive charge on an electronegative element, but a negative charge on carbon atom. But still, since the conjugation is spread over a larger space, then in this structure this compound will have a higher resonance energy. इस स्ट्रक्चर में देखो, अगर आप ऑक्सीजन के पास कोई भी चार्ज डेंसिटी नहीं आ रही है, ना पॉजिटिव ना नेगेटिव, सिर्फ कार्बन एटम्स ही हैं और ये दोनों भी इक्विवेलेंट फॉर्म्स हैं. ठीक है, या तो लेफ्ट की तरफ जब जाएगी इलेक्ट्रॉन डेंसिटी तब ये चार्ज सेपरेशन होगा. व्हेन द इलेक्ट्रॉन डेंसिटी शिफ्ट्स टुवर्ड्स राइट साइड, दिस विल बी द contributor. So both these contributors are equivalent forms, but still the resonance energy of the first structure is higher because the extent of delocalization is more in structure A. This was structure A, then in structure B. That's why resonance energy is higher. Resonance energy higher in A structure and B structure has lower resonance energy. Now we have these two questions. अब आपको इन दोनों में बताना है किसकी रेजोनेंस एनर्जी ज्यादा है. इधर तो आपको पता ही है, ये कार्बोक्सिलेट आयन है, ये ब्यूटाडाइन है हमारा. ओके, सो इफ यू हैव टू ड्रॉ द रेजोनेंस कंट्रीब्यूटर ऑफ ए स्ट्रक्चर, यू गेट an equivalent form of carboxylate anion. These two are the resonance contributors of the carboxylate anion, both of which are equivalent forms only. Equivalent forms. Okay. Here, if you see, you can draw a resonance contributor. So here, if you can see, this is the butadiene, and we can draw the resonance contributor by shifting the pi electron density from one carbon to the sigma bonded carbons. Okay, so when we shift the pi electron density towards the right, we get positive charge on first carbon and negative on the fourth. Or we can simultaneously draw another contributor by moving the pi electron density towards the left, because here we do not have any electronegative element, so we can move the electron density anywhere. So then in that case we have the negative charge on the first carbon and positive on the fourth. Sorry. So these two are the resonance contributors along with the neutral structure, uncharged structure. Okay, so if I label it as 1, 2 and 3 contributing structures, then you can say that B has three different resonance contributors, all three of which have different stabilities. Okay, these are not equivalent forms. So let me write it. Stable contributor of, which is labeled as the first structure. Okay, the other two structures, the second one and third one, are not stable because they have their charges separated. Okay, while if you see in structure A, there are two equivalent forms where the negative charge resides on the more electronegative element. Okay, so of course structure A is more stable. If you are wondering why structure A has more resonance energy than structure B, even when structure B has 3 resonance contributor but A has only 2. So you should know that I wrote in the previous slides that number of stable contributing structures matter in deciding the resonance energy. Okay. B structure has 3 resonance contributors but A has only 2, but still A has a higher resonance energy because the contributors are stable and equivalent. In B structure, only one contributor is stable, the other two contributors are unstable and contribute very little to the resonance hybrid. Okay, so this you should know. So we have covered the stability of contributors today. In the next classes, we will be studying the aromaticity, aromatic systems, anti-aromatic systems and different applications of it. But the next video will include hyperconjugation, okay? And acidity basicity is a very important concept in which you apply all the topics that I have taught in GOC so far, okay? So I'll make a separate video on acidity and basicity. So thank you so much for watching. Let's meet in the next video with hyperconjugation. And yes, please subscribe to my YouTube channel if you have not already.